Hi everyone, in this video I want to give an introduction to the three different gas laws in addition to Boyle's law. So we're going to talk about Charles' law, Gay-Lussac's law, and Avogadro's law. Let's talk about for Charles' law. So Charles' law is all about the relationship between volume and temperature. Now Jacques Charles noticed that volume and temperature have a directly proportional relationship. And what this means is when you have an increase in temperature, you also have an increase in volume. And when you have a decrease in temperature, you also have a decrease in volume. Now, when he actually graphed out all his data points measuring the different temperature corresponding to the volume, his graph actually shows a straight line going towards zero, just like this. Now, using the graph, he derived an equation, and how he went about that is this. He took the volume and its corresponding temperature. He took volume divided by that corresponding temperature, and what he found is that he found it to be a constant that he named K. So this is a constant that he derived from this graph right here. Then he takes another volume, number of volume and its corresponding temperature. He finds that the ratio gives you the same constant, and it's the same constant K. It's the one that's the same as the first calculation. And he found that, in fact, any combination of these volume and temperature give the same value for K. So the same number of constant. So then since V1 over T1 is equal to K, V2 over T2 is equal to K, you can actually set V1 over T1 equal to V2 over T2 because they are both equal to K. And this is actually what we get at the end. And this is what we call a Charles law. And this equation we are going to use to solve some of the problems. Now let's see how you can actually use this law to your advantage. Now first of all, because this is between volume and temperature, we have to establish what unit of temperature is necessary for this equation to work. And all temperature must be in kelvins. So Celsius and Fahrenheit will not work. If a problem gives you something in Celsius or Fahrenheit, you have to always 100% convert that to Kelvin if you want to use this law. In fact, most of all gas laws will require you to convert your temperature to Kelvin in order for the equations to work. Let's take a look quickly at an example. Now I have a 2-liter sample of air, and it's collected at 298 Kelvin. And then cool down to 278 Kelvin with a pressure constant at 1 atm. Whenever something says constant, it just means that it doesn't change. So it stays constant. So the pressure throughout this whole thing where the temperature is cooled down, the pressure stays the same. And the question asked you is, what is the new volume? Now, just like always, we have to identify what is it that's given to us. And the first thing that's given to us is V1. Now V1 is 2 liter. That's what we start with. So remember V1 T1 or anything that's with the subscript 1 mean that it's something we start with. 2 is what we end with. So let's look if we have T1. In fact we do have T1. T1 is 298 K. And then V2 actually we do not have, and that's actually what is asked of us. So the new volume here is V2. T2, the other variable in our equation, is given to us right here when it says then cool to 278 Kelvin. That's our T2. Now, since V2 is what we're looking for, you can rearrange this equation to solve for V2. And you're going to do that by multiplying both sides. So this side and this side both by T2. And that actually gives you this little rearrangement. Then you just plug in a number and solve. So T2, it's 278K times V1. V1 is 2 liter. T1 is 298K. And you plug that in. And there you go. 1.9 liter is your final answer. And what this means is that the volume decreased from 2 liter to 1.9 liter if you cool it from 298 to 278. So that's what that means. Let's talk about Gay-Lussac's law now. And Gay-Lussac's law is all about the relationship between pressure and temperature. So what he did was he has two containers having the same amount of gas and the same identity of gas as well. So it's the same gas. And so the first one he would name, that's P1 and T1. Those are, the stuff that he started with. And then he changed the condition of how this gas was in. So for example, he changed the temperature by heating it up. So that becomes our T2. And then because of the change in temperature, there's also change in pressure, and that's now becoming P2. Now, once he get all the data points for this experiment, he finds that actually when he takes the ratio between P1 and T1, which is what he starts with, he gets a constant that he named K. Now, this constant is derived from the graph, just like Boyle's law and just like Charles' law. Then he takes the ratio of the sample that he changed, the condition has been changed, and that's becoming P2 and T2. The ratio of that he found to be also K, which is the exact same constant as P1 and T1. Now, this shows that any combination of pressure and temperature actually gives the same value for K. So, just like before, we can actually set P1 over T1 to be equal P2 over T2 because they are both equal to K. So, this is actually the form of the Gay-Lussac's law that you will use for your calculations. Now let's take a look at how you would actually use Gay-Lussac's law to solve a question. So this question says a sample of gas at 15 degrees Celsius and 1 atm of pressure is heated to 50 degrees Celsius at a constant volume. Now what is the new pressure after you heat it up to 50 degrees Celsius? So like always, let's identify what it is that we have. Now, I want to use Gay-Lussac's law, and these are the four different variables in his law. Let's first identify, do we have P1? Indeed, we do. Now, P1 is 1 atm. That's what we start with. T1 is what we start with, temperature temperature-wise, and that's 15. And we always have to convert it to Kelvin, because if you keep it at Celsius or Fahrenheit, you'll find that the calculation will be off, because all these gas laws are based on temperature that is used in the unit of Kelvin. Then next, let's see if we have P2. We do not. And in fact, that is actually what we are asking. They are asking of us. So what is the new pressure? That's P2. T2 is our 50 degrees Celsius, and that is also converted to Kelvin. So, like before, I want to rearrange this little gas law in order to solve for P2. So in order to do that, I am actually going to multiply both sides, so P1 over T1 and P2 over T2, both sides by T2, giving me this equation. And then all you got to do is plug in the numbers and solve. So P1 is 1 atm, T2 is 323 Kelvin, and T1 is 288 Kelvin. And when you punch that in the calculator, keeping in mind a significant figure, you should have 1.12 atm as your result. Now this shows that the pressure rose from 1 atm to 1.12 atm when you heat this gas up from 15 degrees Celsius to 50 degrees Celsius. Okay, lastly, let's talk about Avogadro's law. And it's all about the relationship between volume and moles. And Avogadro found that volume and the number of moles of gas actually have a direct relationship. What this means is that the more moles of a gas there are, the more they take up in terms of volume, with the condition that they have constant temperature and pressure. Now, a given number of moles also takes up the same volume regardless of what kind of gas it is, meaning that it could be helium, oxygen, or hydrogen. A given number of moles of each of those gas will take up the exact same amount of volume, and we actually know what amount of volume 1 mole of any gas can take up, and that is, go ahead and answer the question now. Hopefully you chose 22.4 liter. That's right, that's from our previous chapter. 1 mole occupies 22.4 liter. Now let's talk about how you would derive Avogadro's law. And what happens is that when he took the volume number corresponding to a mole number, he finds that the ratio equals to K, which is a constant that derived from a graph like this. And then after changing the condition of that gas, just like how Gay-Lussac did, he found that the new volume and the new mole also gives him the exact same constant, and in fact the same one as before as well. So any combination of the volume and a number of moles gives the same value for K. So like before, we can set V1 over N1 and V2 over N2 to be equal to each other because each of them is equal to K. So this is actually the form of Avogadro's law that you will need to use for solving problems. It is also good to note that you are responsible for this graph and understanding that this means that there is a directly proportional relationship between numbers of moles and volume. And let's see how we actually solve a problem using Avogadro's law. Let's suppose we have here 12.2 liter of sample containing 0.5 mole of oxygen gas at a pressure of 1 atm and 25 degrees Celsius. If all the oxygen is converted into ozone, O3 at the same temperature and pressure, then what will be the volume ozone form? Now this is our Avogadro's law. Let's look for what is it that we are given in terms of these variables. So variable number 1, V1, let's start with what we have. What do we have in the beginning? We have 12.2 liter in the beginning. And then N1 is what the mole number we have in the beginning, and that is 0.5. V2, do we have V2 after oxygen is converted at the same temperature or pressure, but I was not given the volume after this reaction. So V2 is what is it that the one I'm being asked for. Then N2 is also actually I do not have. I just have that after this reaction, I know that it has the same temperature and pressure, but none of those temperature and pressure is not in our little equation here. So what should we do? Step number 1. First step, if you don't know two variables, first let's just tackle one at a time. So step 1, find out how many moles of ozone will be made from O2 gas. And you do that by our favorite topic, which is stoichiometry. Well, first of all, you got to balance this equation. O2 going to O3. When you balance it, you get 3 moles of O2 becoming 2 moles of O3. And you know that in the beginning, you have 0.5 moles of O2. And then you do your stoichiometry using the mole ratio between O3 and O2, giving you 0.33 mole of O3. So this is how much moles of O3 that's created after this reaction here. Oxygen is converted into ozone at the same temperature and pressure. Now knowing that, that's my N2. So then knowing my N2, I can now have this new set of information with my N2 now being known. I can actually now rearrange this Avogadro's law equation to serve our purpose, which is to solve for the final volume, and the final volume is V2. So let's go ahead and do that. Rearrange the equation, and this is what I get when I rearrange this equation. It's by simply multiplying both sides by N2. And then you plug and chug, as I like to call it. You plug in each of these variables, and then you get 8.1 liter. So what this means is that 12.2 liter O2 become 8.1 liter O3 at constant temperature and pressure. All right, that concludes this video.